Welcome to Free Pilot Training. I'm Josh. If you're looking for an excuse to throw away your flight computer and still make flight calculations, you're going to love today's video. This is also a great excuse to purchase that calculator watch you've always wanted.
You know you want one. Not only will these skills eliminate your need for a flight computer, but you're also going to find them really useful for everyday flying. I even use them sometimes in the C-130, even though the plane makes a lot of calculations for me. Now the main calculations I want to focus on today are time, fuel, and distance calculations, because these are what you'll be using even after you get your pilot's license, but we'll discuss how to make the other calculations that you'll find on the flight computer as well. When we're talking about calculating time, fuel, and distance, we're actually talking about two different types of calculations, not three. We're trying to find the relationship between distance and time and between fuel and time. Both of these types of calculations use time as a system of measurement. When we talk about the rate at which we do something, we typically talk about hours. For example, I'm driving 100 miles an hour, or I'm burning 10 gallons of gas per hour. But hours are really not a small enough measurement to get accurate numbers for flight, so we typically use minutes to calculate those things. Now, we all know that there's 60 minutes in an hour, so if we want to convert between hours and minutes, all we need to do is multiply and divide by 60, and this is what we call the 60-to-1 rule. We're simply changing things from hours to minutes to make things simple. Let's jump right in so you can see what I'm talking about. The first calculation we're going to be making today is to determine how fast we're traveling. Let's say we flew for 2 nautical miles and it took us 3 minutes to get there. How fast are we going? Okay, so we want to know our speed in relation to hours, but what we have is our speed in relationship to 3 minutes. Well, that's not useful for anyone. The first step in solving this problem is to figure out how far we went in 1 minute. So if we want to figure out how far that is, we simply divide 2 by 3 minutes. Now we can see that in 1 minute we're traveling 0.67 nautical miles. We're traveling about 0.67 nautical miles a minute. Well, what about per hour? Well, there's 60 minutes in an hour, so we simply multiply by 60 to see that we're traveling 40.2 nautical miles per hour. And this is the whole basis for the 60-to-1 rule. The first step is always finding your relationship to 1 minute. Then the problem becomes a lot easier to solve. Okay, what if I flew 100 miles and it took me 50 minutes to get there? Now how fast am I going? Once again, the first step is to figure out how far we went in 1 minute. Well, 100 miles divided by 50 minutes is 2, so I'm traveling 2 miles a minute. And you probably don't even need a calculator to see that 2 miles a minute times 60 minutes is 120 miles per hour. Now you're starting to see how easy this is, but let's make things a little bit harder. What if I want to know how long it will take me to get somewhere? Let's say I'm flying 110 knots and I'm traveling 130 nautical miles. How long will my trip take? Well, 110 knots is 110 nautical miles per hour, so let's change that to minutes by dividing by 60. So we're traveling 1.83 nautical miles a minute. Now that I know that, I can see that all I have to do is divide 130 nautical miles by 1.83 to see that it should take us 71 minutes to get there. By the way, I'm doing a little bit of rounding on all these calculations today, so if your numbers are slightly off, that's why. But if I wanted to get these numbers down to the nanosecond, I could do that if I wanted. Speaking of that, here's a great way to use this calculation in the airplane for some really quick pilot math. Let's say I'm flying 118 knots ground speed and I've got a 308-mile trip. How long is that going to take me? If I'm looking for a really quick answer, this is how I'd tackle the problem. You and I both know that 2 hours is 120 minutes. So I can easily look at 118 and know that I'm traveling about 2 nautical miles a minute, even without using a calculator. Then 300 miles divided by 2 is 150. Then 8 minutes divided by 2 is 4, so it's going to take me at least 154 minutes to get there. And even with all this rounding, my quick calculations are getting me within 3 minutes of an exact answer. And as you can see, this can come in really handy in the plane when you need fast answers. And I didn't have to dig out my flight computer. I use the 60-to-1 rule for problems like this all the time. Now, what if I want to know how far I went? Let's say I'm traveling 80 knots for 1 hour and 40 minutes. How far did I go? Well, how many nautical miles in a minute are we traveling? 80 divided by 60 is 1.33. So I'm traveling 1.33 nautical miles a minute. Now, how many minutes am I flying for? 1 hour and 40 minutes is 100 minutes. So I simply multiply 100 minutes by 1.33 nautical miles a minute to see that I traveled just over 133 miles. I didn't even need a calculator for that part. I just moved the decimal over. What if I'm traveling 90 knots and I flew for 1 hour and 10 minutes? Now how far did I go? Well, I don't even need a calculator to see that I'm traveling 1.5 nautical miles a minute because 90 divided by 60 is 1.5. An hour and 10 minutes is 70 minutes, and 70 times 1.5 is 105. So I'll travel 105 miles. Next, we're going to be talking about calculating fuel. And just like I mentioned in the last video, before we can accurately make calculations, we need to check the POH to see how much fuel per hour we can expect our airplane to burn. Okay, so let's say our POH says we're going to be burning 7.5 gallons per hour. What if I fly for 43 minutes? How much fuel will I use? Just like our distance calculations, we need to change this number to minutes to make things easier on us. So 7.5 gallons per hour divided by 60 is 0.125 gallons per minute. Now we can just multiply that times 43 because we're flying for 43 minutes. Looks like we'll be using about 5.4 gallons of fuel. What if I'm burning 10.5 gallons per hour and I'm flying for 15 minutes? Looks like if we convert 10.5 gallons per hour over to minutes, we're going to be burning 0.175 gallons per minute. So in 15 minutes, we will have burned 2.625 gallons. Let's change this around a bit. Let's say I have 32 gallons of fuel on board and I'm burning 9 gallons per hour. How much flight time do I have? There are a few different ways to solve this one, but the easiest way is to simply divide 32 gallons by 9 gallons per hour, and that gives us 3.56 hours. So if we want to turn 0.56 into minutes, we simply multiply that times 60. That gives us 33.6, so we'll have about 3 hours and 33 minutes of fuel on board. Now, let's say I flew to another airport with full tanks and it took me 45 minutes to get there. When I landed, I went ahead and topped off the plane with more fuel and it took 7.5 more gallons. How many gallons per hour did I burn on that trip? This one's a little bit tricky, but if we divide 7.5 by 45, we can see that we're burning about 0.167 gallons per minute. If we multiply that times 60 minutes, you'll see that we're burning 10 gallons per hour. Okay, now that you've seen these basic calculations, let's solve a couple cross-country problems. Let's say we're flying across country from Veneta Municipal over to Branson West. After our departure, we crossed our first waypoint at 0813 local time. Then we flew over our second waypoint at 0821 local. What time will we arrive at our destination? Before we can calculate anything, we need to find our distances. And we can do that by using our plotter. As you can see, the distance between our first waypoint and our second waypoint is 13 nautical miles. And it looks like we have 50 miles to go for the rest of the trip. If we subtract 813 from 821, you can see that it took us 8 minutes to go 13 miles. So, how many nautical miles a minute are we going? Well, if we divide 13 by 8, you can see that we're traveling 1.625 nautical miles a minute. Now, you could multiply that times 60 to get your ground speed of 97.5 knots, but we don't need to do that in order to answer this question. All we need to do is divide our distance remaining by our nautical miles per minute. So if we divide 50 miles by 1.625, we can see that it'll take us exactly 30.77 minutes to get there. And 0.77 of a minute is roughly 46 seconds. So we'll get there in 30 minutes and 46 seconds. If I want to know my time of arrival, I can simply add this time to the time at my last waypoint, which we said was 8:21. So you can see that we'll arrive at West Branson at 8:51 and 46 seconds. Now, how much fuel will we burn for the rest of the trip? Well, if the POH tells us we're burning 8.2 gallons per hour, let's change that to minutes really quick. 8.2 divided by 60 would mean that we're burning 0.137 gallons per minute. And that means we're going to burn 4.22 gallons of fuel before we land. Let's do another one really quick. Let's say we're flying back and we pass our first waypoint at 0914 local. and we pass our second waypoint at 9:22. This leg is 10 miles and we have 51 miles to go. Now what time will we arrive at our destination? As you can see, if we subtract 9:14 from 9:22, this leg took us 8 minutes as well. We must have a bit of a headwind now. Anyway, let's see how many miles per minute we're going. Remember, all we have to do is divide our distance by our time. So we can divide 10 by 8 to see that we're going 1.25 nautical miles a minute. Now we simply divide our distance remaining of 51 miles by 1.25 nautical miles a minute to see that we'll arrive in 40.8 minutes. So that's 40 minutes and 48 seconds. Let's add that to 9:22 and you can see that we'll arrive at 10:02 and 48 seconds. I changed my power setting for the route back. Now my POH says I'll burn 8.4 gallons per hour. If I divide that by 60, you can see that I'm burning 0.14 gallons per minute. Multiply that times our 40.8 minutes, and you can see that we'll burn 5.712 gallons for the remainder of this trip. Now, based on my calculations, at this waypoint I had 10 gallons of fuel remaining. Am I going to be legal to continue this flight to my destination, or should I consider diverting? Well, we know it's daytime because of the time, so we need to land with 30 minutes of fuel. We're burning 8.4 gallons per hour, so we need to have half of that when we land. So we need 4.2 gallons in the tank when we land. Okay, so we have 10 gallons in the tank, and we're going to burn 5.712 gallons the rest of the way. That means we'll land with 4.288 gallons of fuel. So to answer our question, will we be legal? Yes, but barely, and you should never be cutting it that close. But you never know the situations that you could get into, so it's good to be able to make these calculations. Because of that, it's smart to continue practicing making calculations like this, because after you get your license, you will need to use them in flight occasionally. Now, here's something a lot of people don't know. You can actually make your wind calculations without a flight computer as well. And while it's a little easier to learn how to use the whiz wheel to make these calculations, once you learn how to do this, you can use this method to make quick estimates that are fairly accurate and save you from having to dig out that flight computer in flight. As you know by now, if there's no wind, the ground track or magnetic course your airplane is flying will be the same as your heading, minus deviation. In addition to that, your ground speed will also equal your true airspeed. But as you and I both know, there is always wind. Without a flight computer, one way you can determine your wind correction angle and your ground speed is by using a wind triangle or vector analysis. Let's say you want to fly a true course of 100 and you're planning on flying at 85 knots true airspeed. You looked at the winds aloft and it looks like the winds are going to be 060 at 15 knots. To solve this problem, you need two simple tools, a protractor like you use in middle school and a plotter. The first thing we need to do is lay the protractor out on your chart in a line with true north. Remember, lines of longitude all run directly north and south, so let's draw a line here going north and south so it's easier to see. And I'll go ahead and label these to make it Army proof. Now, we know our winds are 060 at 15 knots, so let's draw a line from the 60-degree mark through the center of the protractor. And this needs to extend past the other side a little ways, and you'll see why here in just a second. Next, let's pull out our plotter and make a mark from the intersection of those marks down that wind line 15 nautical miles, because our wind speed is 15 knots. Once we do that, we can take the plotter and place one end on that mark and place the other end on your true course. You want the true course to intersect the true airspeed you're expecting on the plotter. In this example, I'm expecting 85 knots, so I'll make a mark here on my true course, then I'll draw a line between these 2 points. From here, if I want to know my ground speed, all I need to do is measure our true course line back from our intersection over to that mark where our vector line intersects. I'm reading 72 knots ground speed here. How about you? Now that we've done that, this line represents our true heading we need to fly to keep our airplane on our true course. Now, to find out what that heading is, we need to pull our protractor back out. To make this a little easier, let's zoom in on where these two lines intersect. And when we lay the protractor down, you can see that our wind correction angle is about 7 degrees. And as you can probably tell, that's 7 degrees we need to point our nose to the left to keep us on our true course of 100. And as you know, the numbers on a compass get smaller as we turn to the left. So all we need to do is subtract 7 from 100 to get our true heading of 093 degrees. But don't forget to include that magnetic variation in your calculations. Today, we'll say mine is 2 degrees east, so I'll subtract that to get a magnetic heading of 091 degrees. And as you can see, we got our ground speed, our wind correction angle, our true heading, and our magnetic heading without even pulling out a flight computer. And I think that's pretty cool. Let's do one more of these with a tailwind so you can see the difference. This time we're flying a true course of 082 with a true airspeed of 80 knots, and our winds are 234 at 15 knots. Once again, we'll draw our north-south line and label them for our Army guys. My Marine friends probably need this too. Anyway, from here it's kind of weird because this protractor doesn't have a backside, but that's okay. I can do a little math here to see that the reciprocal of that number is 54 degrees, and I'll draw my line like it's trying to push my airplane over to the other side of that course. Then we'll grab that plotter and make our mark 15 knots from there. I'll draw my vector line using my true airspeed just like I did before. This time my true airspeed is 80 knots. Now our wind triangle is complete. Let's grab our ground speed by measuring our true course again from our north-south intersection over to this one. And it looks like I don't have enough plotter for this job, so I'll just grab another one, and now I'm reading about 92 knots ground speed. Let's zoom in a little bit and grab our wind correction angle. I'm getting 5 degrees to the right on this one, so I need to add 5 degrees to my true course when I fly to get a true heading of 087 degrees. And once again, we'll subtract our easterly variation to get a mag heading of 085. Now while this method takes a tiny bit more work than a flight computer in the beginning, using this method will allow you to see how your wind speed and direction affects your heading and your ground speed. And you can actually get really accurate estimating your ground speed and heading with just a tiny bit of practice. So try this method a couple times and see if you like it. Let's go back and look at conversions for a minute. To completely eliminate the need for a flight computer, there are a couple more things you should know how to do. First, you need to know how to find density altitude. And as I mentioned in the past, you need to find your pressure altitude first. And even the old whiz wheel doesn't do that for you. To find that, you need to know your field elevation and the current altimeter setting. Let's say your field elevation is 732 feet and the current altimeter is 28902. To find your pressure altitude, all you need to do is take the standard altimeter setting, which is 29.92 inches of mercury, and subtract the current altimeter setting from that. Now, keep in mind, sometimes this number will be negative, and that's completely normal. In this example, our answer is 1.00. Now, because the pressure in our atmosphere drops 1 inch of mercury every 1,000 feet, let's turn this into thousands by moving the decimal over 3 places. It looks like we need to add 1,000 to 732 feet to get a pressure altitude of 1,732 feet. If this number was negative, then I would subtract that from the field elevation instead. Okay, so now that we know our pressure altitude, let's find density altitude. The easiest way to do this without a flight computer is to use a spaghetti chart like this. This one comes from the Pilot's Handbook of Aeronautical Knowledge, which you can actually download for free from the FAA's website, or you can get the book pretty cheap from Amazon as well. I'll put links to those in the description. You also find these a lot in newer POHs. So now you can see that the only two things we need to find density altitude are pressure altitude and the current temperature. Let's say that the current temperature is 35 degrees Celsius and we just said that our pressure altitude was 1,732 feet. So let's find 35 degrees down here at the bottom and move up until we hit a pressure altitude of 1,732. As you can see, we kind of have to guess where that is, and we simply move over to find our density altitude of about 4,500 feet. Now, there is a way to solve this without one of these charts. You can use this formula too if you want. I'll do this really quick for you, but no one's going to expect you to know how to do this. So we've got a pressure altitude here. This is our outside air temperature, which we said was 35 degrees, and this isotemp is the standard air temperature at altitude. Remember, standard temperature at sea level is 15 degrees Celsius, and the temperature drops 2 degrees every 1,000 feet. So if our pressure altitude is 1,732, standard temperature there is about 12.3, not 15 degrees. Okay, so let's do this math really quick. 35 minus 12.3 is 22.7. Multiply that times 120 to get 2,724. And we'll just add that to 1,732 to get 4,456. So our exact density altitude is 4,456 feet. And this is what you're going to be using to calculate the performance of your airplane. As you can see, our density altitude chart was pretty close, but if you're trying to get exact numbers for some reason, this is the way to go. Okay, so another thing you might want to convert is true and calibrated airspeed. Now, I'm going to be the first one to admit to you that if you want to be precise, all the formulas you're going to find are way too complicated. You're much better off using a flight computer to get the numbers perfect. But here's a quick wag that'll get you pretty close. For every 1,000 feet of altitude that you gain, you can generally expect your true airspeed to be about 2 knots faster than calibrated airspeed. For example, let's say I'm flying at 120 knots true at an altitude of 5,000 feet. Every 1,000 feet of altitude, I'll add 2 knots. So let's multiply 2 times 5 because we're flying at 5,000 feet, and that gives us 10 knots. Now, we said our true airspeed was 120 knots. So we simply subtract 10 from 120, and that gives us 110 knots calibrated airspeed. If we knew our calibrated airspeed, but not our true airspeed, we'd simply add this number instead. For example, if my calibrated airspeed was 100 knots, then I'd add 10 to that to see that I'm going about 110 knots true. Let's do one more of these really quick. Let's say I'm flying at 10,000 feet pressure altitude at 90 knots calibrated. 10 times 2 is 20, so we're looking at a difference of 20 knots. We know our calibrated airspeed is 90 knots, so our true airspeed should be about 110 knots. What if we were flying at 130 knots true? Well, in that case, we'd simply subtract this number. In that case, our calibrated airspeed would be about 110 knots. Now, once again, if you pull out the flight computer, you're going to notice that these numbers aren't perfect, but this is one of the best methods out there to get you a quick estimation without a flight computer. The last thing you'll find on an E6B is a way to convert between true and calibrated altitude. Now, as you may remember, this is important because the altitude you read on your altimeter may be slightly different than the altitude you're actually at because temperature and air pressure can affect the readings on your altimeter. Now, while it is possible to convert between true altitude and calibrated altitude with a little bit of math, the best method out there is to find this chart in section 7 of the AIM. While this chart doesn't give you precise numbers, you can use it to see how low you could potentially be below what your altimeter is actually reading. Notice up here the numbers across the top indicate your height above the ground, or AGL. So if I'm flying 1,000 feet AGL and the temperature is -10 degrees, my indicated altitude could be as low as 100 feet below my true altitude. So if my altimeter reads 1,500 feet MSL, and there's a tower ahead of me at 1,450 feet MSL, my altimeter may tell me that I'm going to clear it, but if the temperature is -10 degrees, I'm probably not going to be able to clear it. So while you typically don't need to convert between true altitude and calibrated altitude, this chart is the perfect tool to print out and put on your knee board if you're concerned about cold weather affecting your indicated altitude, because true altitude doesn't change. I hope you learned something today. In my next video, I'm going to do something a lot more fun. I plan on flying an actual cross country and only using pilotage and dead reckoning with a navlog to do it. I'll put that video right here when it's available. You're really going to enjoy that one. I'll see you over there.
Folks, you're not going to believe this. I just spotted free pilot training. I think I'll watch it a little bit longer.